Good morning, good afternoon, good evening to all the folks who are joining in, depending on from which part of the world you are joining. Thanks for joining us on the 35th meetup of Kaggle Days Meetup Delhi NCR group. Today we are very much, like I would say, excited to welcome Urvish. So he is a Kaggle Competitions Master, and like he would be talking and taking a session on creating instrument music classification algorithm using deep learning. So, like I was super excited about this event because the domain in which the discussions would be happening today is something which I have not explored yet, and something which is new to me. I hope it would be a useful session and a session full of learnings for all of us. Over to you, Urvish. Thank you.
Yeah, thank you, Ayan, for the introduction and inviting me to Kaggle Days Delhi NCR Meetup. It's my pleasure to be a speaker here. So, first of all, welcome everyone. Good evening, good morning. So it's like morning in Canada for me. So, thank you for joining. And we would start with first like a intro. I have like outlined all of the things that we are going to present, and we will do code walkthrough as well, so that I would like to show you guys the code and how things are done and so on. Of course, I would add some of the you can say tips and like tricks from the previous Kaggle competitions, which were on audio classification, or recently there was a competition, Bird Clef 2022, which is also more or less in similar domain. Let's begin. So, first of all, my introduction. I am Urvish Patel. Currently, I am doing my Master of Engineering from University of Windsor in Canada. I am also Kaggle Competitions Master, as you already guys know. And then I do like a lot of freelancing work these days on Upwork. So that's basically my introduction. This is my Kaggle profile. You guys can connect with me on LinkedIn, maybe follow me on Kaggle, and hire me if you want for your freelance work. So yeah, that's for my introduction. Uh, Okay, so this is the like simple outline that we are going to follow in the this meetup, and we will talk about problem, then little bit of data, then different ways to do EDA, then like actual deep learning for audio classification, then code walkthrough, and so on. Uh, First of all, moving to problem. In simple words, the problem is, as you guys know, creating an instrument or like music classification algorithm using deep learning. So basically, you can have like different musics, right? Like jazz, rock, or and like hip hop and so on, and they can be played with different instruments like flute, maybe guitar, electronic guitar, and so on. So the idea is that given a sound of a music, you have to identify which instrument is playing. It can be jazz played with organ, so you have to identify whether it's organ or not. In Kaggle, like the recent competition, which was a Bird Clef 2022, the idea was to identify the bird from the bird call. So more or less the domain is different, but the idea is similar. Like you have given a sound, and it can be like bird call, it can be musical sound, and so on, and you have to classify that into some bucket based on the problem statement that we are facing. Here we are going to classify them into instruments. So as I said, it can be flute, organ, or cell, and so on, and we will see all of the different instruments which are present into the data set. Now about the data, the data is taken from IRMS data set for instrument recognition in musical audio signals. It's like a open source data set, and considered as one of the benchmark in instrument classification. So the link is there. You guys can go there and check out other details. There are a lot of other details like how they collected the data, and many other information related to the data set. But I would say the most important part for us would be understanding how many different instruments are there. So it has like a cello, clarinet, flute, acoustic guitar, electric guitar, organ, piano, saxophone, trumpet, violin, and a human singing voice, which is like just voice. So these are like a different instruments, you can say, or different sounds that we are going to listen to. But one other thing is they also have classified them into different music categories. So you would see like a jazz, rock, hip hop, and so on as well. as well as like there are going to be intersection of two instruments, so there is possibility that the cell and organ might be getting played in the same music, and so on and so forth. So the annotations are like this. Here we can see like the cell. Let me get to so it's like a cell. Then we also see like pop rock, so which says like it is pop rock music, and so on. We will see like more details of the same thing in, I think, let me go back to the Kaggle notebook. Yeah, so we are gonna also like do say the things at the same time, I would say, like little bit of data, like slides, and like actual seeing the code and data itself. So let's see like CLA music. So you see like a lot of different data points are there, and then like when we move to, let's say, flute, we see again flute, a lot of flute data points are there. And you see like there is a combination of flute and other instrument as well, and the same thing is gonna be there. Like each of them will have like a different sort of overlapping. Here you can see voice and DRU, which is I think for drum, and so on. So each of the sound can have like multiple labels, you can say in one way, and a single label as well. So now, a similar line of thing was there in Kaggle competition as well. If you go to Birdclef, and you will see the labels are similar to that. They have like primary and secondary labels. Basically, similarly, we have like two instruments. So we can say one instrument, which is the dominant, is a primary label for us, and like the other instrument, which is like there, but it is not considered as the main label, is like secondary label, and that can be used as label as well. We can like use primary label with say 0.95 as a like weight, and like use the secondary label as like a 0.05, and so on. So that's like sort of a trick to add more than one type of sound into your labels, and then like training your model so that it can know like differences of like having two sound or single sound, and so on. Now moving to the next slide. So the EDA is gonna be like very simple. Like there are different tricks or like different ways you can visualize a signal. So one is like visualizing it in very like simple waveform sound. So waveform is basically visualizing the amplitude of a signal with respect to time. Then like it's like a just you, from here you can see like there is a difference between the amplitudes of these two sounds. Of course we are going to see this in the code as well when we move there. And then there is like one more thing you can do, like is STFT. We will talk about this in code as well. Then you can do like mil spectrogram, or you can do like a normal spectrogram. You can do like fast Fourier transform, which is like FFT as well, and so on. Now let's go to the code, I would say. I would start the notebook, and like this is gonna be we are gonna like do three things.
Urvish, just a request, if you could zoom a little bit, maybe it would be great
Yeah,
for
sure.
community members. Yeah, works. Thank you. No, like it got a little bit more. So yeah, it works. Thank you.
Yeah, it's good. Okay.
Yeah.
uh, it seems like it is taking a little bit time to start, but here you can see like a simple doing matplotlib inline to visualize the plotting, and then we are importing some of the libraries that we need. IPD or like IPython displays sort of displaying visualization or like plots in the IPython notebook. Then librosa is one of the most used library, I would say, when it comes to audio processing or sound processing in Python. It has, I think, all the things that you might need, like loading your files like MP3 or WAV files, then doing STFT or FFT, or generating mil spectrogram, or maybe converting it to from power to decibel or decibel to power, and so on. We are also importing like a display module of Librosa, which is to display different sounds or mil spectrogram for us. Then we are importing our two oldest friend, NumPy and Pandas, and we are importing OS module in case if we need it. Now, one of the thing is like a sampling rate or like sample rate. So it is like telling the library you are defining that on what sample rate we are going to sample our data. So basically in music, considering like, it's like the 44,100 is like considered as a good sampling rate. So that is why we are defining sampling rate. Depending upon sampling rate, the sound or like the signal itself can be changed, or like I will show you the plots, like when we change sampling rate, the plots and everything is also getting changed. So basically when you use higher sampling rate, you sample more data points, or you can say like more points from the audio itself, and you get like bigger like waveform or like bigger signal. When you sample like a small or like use small sampling rate, you have like a smaller waveform and so on. So this sampling rate works well as per the one of the person whom I know, who is like a sort of music producer. Here we are defining the path to our first file, which is like cell, and you can see like the other instrument is here as well, which can be like our secondary label. And then the file extensions are usually WAV or MP3. WAV files are like standard when it comes to working with like the audio in deep learning or machine learning. Here we're defining just like figure size, and then we are doing librosa.load. So Librosa has like this very simple method to load the any type of sound. It's like a WAV file, so it will load the WAV file for us. It will use this sampling rate, which is like we defined on the top. And when it loads into two, it gives like tuple. In the tuple we have like data and sample rate. So data is gonna be like NumPy and D array, basically NumPy array, and that's gonna be like, I would say, our main thing, or like a focus like part which we are gonna focus more. And then we are going to use like this display, which basically does the waveform plot. Like librosa.display.waveshow. Waveshow basically shows the waveform plots of the signal or audio file that we have, and we will also do like IPython display to display the audio. So let's execute this one, and you get like sample rate. Just I printed that down, and you see this is from the IPython audio display. So basically giving us chance if you want to play the sound or not. And here we get this nice waveform plot for our audio file. And we see like the y-axis is between like 0.10 to 0.-10, and on the x-axis we have time, so it starts from 0 to up to 3, basically from 0 to 3 seconds. So x-axis is going to be always in seconds, and like the y-axis is the amplitude of our signal. So the signal varies between -10 to like +10 amplitude. I'm not sure if you guys are going to be able to hear this, but let's say we play this. You guys heard that, right? Or I'm the only one who is able to hear this?
I think maybe it's audio in the computer. Maybe it doesn't sound
Yeah.
in StreamYard. No
Yeah.
worries.
Yeah, no worries. Yeah. Now let's see if we visualize the other instrument, and what do we have here. So the sample rate is same, but now you see the waveform is like a bit different. Like it's like first of all, like the amplitude on the y-axis has changed from -15 to +15. So there is like a, I would say, like a 50% increase or decrease in the amplitude. The x-axis is going to be same because it's like time axis. All these files are of like 3 seconds, so like the x-axis hasn't changed. But the plot, you can see like the waveforms are like very different from this sound. It's like in the first sound, the waveforms are like not moving too much for like up to like 1.5 second, and then we saw like a little bit of move here, and here we are seeing like they are moving ups and down between like positive 10 to negative 10, and then we see like a very bumpy sound here at 2 seconds. So it clearly shows that there is like this sort of variation between two instruments. The amplitudes are like getting changed a lot, and so on. uh, and this is like useful, and when we do analyze, because we know like higher amplitude means the instrument might be like CLA and so on, and cell or like water and so on. And then the next, or I would say like the most used plot would be STFT. So STFT is like the full form is like a short-term Fourier transform. So before we talk about STFT, it's like obvious to talk about Fourier transform itself. So as we know, like Fourier transform is basically a transformation which is used to convert from time domain to frequency domain. So all the signals, the waveform plot we saw, it's like just amplitude versus time, but there is no information about frequency of this sound. We don't know like at what frequency it is, or like what sort of variation it has on frequency domain. And when it is sound, it's like obvious to have like different frequencies and like some different representation when it comes to frequency domain than the time domain and so on. And so the Fourier transform is basically something which will help us converting from time domain to frequency domain. And if we want, like we can do inverse Fourier transform and get back to time domain and so on. And STFT is like short-term Fourier transform. So basically, when we have a signal like this, which is of 3 seconds, what we do is like we divide this signal into smaller chunks of equal length, and we perform Fourier transform on each smaller chunk. So basically converting smaller amplitude versus time domain to frequency versus time domain, so that we know like a smaller information or like a smaller details related to those frequencies which are present in those domain. That's why we do a short time Fourier transform, which is like STFT, and basically we divide on different window length. So it's sort of like you can say in OCR we know that slide moving window algorithm, which is like a sort of moving perfect, like a perfect window on the entire image to do something. Similarly, STFT does the same thing, but what it does is like it moves a window from one part to another part and so on, and it converts that part or like a particular time frame of their signal into frequency domain for us. And it will like give us all the frequencies which are present. And of course, I mean, one more thing is that Fourier transform converts into frequency domain, but it also gives us sine and cosine waves all the time. So it's like representing any signal or any wave into sine and cosine representation. And when we do this, we will see like some really good plot, or I would say like different plots for this same signal. And there are certain parameters which you can control. First is hope length, then there is like window length. Window length is like determining the size of window which we want to keep, like the moving window that we have. Hope length is another parameter which basically helps us in understanding the overlap between the two windows. So we do not want to miss any of the part when we do the sliding window. So hope length is determining like how much we are gonna like overlap between two windows. So we want like 50% overlap. So hope length is like equal to window length divided by 2. This is like absolute division. And then the label, just like getting the label part. Then again like loading the file. And then we use Librosa STFT. Basically, as I mentioned, like Librosa has all the functions that you might need in order to do any sort of audio or sound analysis. So it has like STFT. We feed our ND array, which we load from librosa.load. Then we provide the window length, like the window length which we want, and we did hope length. So basically, how much overlap we want between the sliding window. Then we need to convert the scale from amplitude to decibel. So basically, we saw the above plots are between time and amplitude, but this time we want it to be between time and frequency domain. So basically, amplitude to dB function will convert our amplitudes to decibels, and decibels are in hertz and so on. So then we will get this spectrogram, you can say, basically, and then we will use again librosa.display spec show to do the plotting for us. And we are doing this in for loop. Basically, we are trying different window length. And why do we do that? From the plots, you will be able to see different window length correspond to different plots. And when we do that, the information is automatically get changed in the plots and so on. Let's execute this cell. So first we use window length of 128. Now you see the x-axis is x-axis is same from 0 to 3 seconds, but the y-axis is in hertz. So it is 20,000 hertz from 0 to 20,000 hertz. So I think from I think 12th class physics, we know that human ears are perceived between I think 20 hertz to 20,000 hertz. So it's I think the same frequency domain that we are seeing over here. And the window length is 128, and because of that the shape of this spectrogram is 65 cross 2068. So based on the window length, the shape of spectrogram is also getting also will change. And when we increase the window length, now you see there is a lot of difference between these two plot. Here we see there are too many frequencies present over here, but when we increase the window length, we are seeing a less amount of points over there, and the information is little bit scattered. Now the shape has changed as well. It's 129 cross 1034. So you can say we can say the size over here is in the first part it's getting double. The shape in first part is getting double, and the number of columns, or you can say 2068, has reduced to half of it when we increase the or when we double the window length. Similar gonna happen when we double the window length again. And again, when we double the window length, the shapes are changed, and the signal itself is you can see it has changed a lot. Mostly I would say a time frame from 1.5 to here up to 2 and 2.15 second has changed a lot. Here we didn't saw that much of gap, but now we are seeing more gaps over here. And similarly on these parts also the gaps are increasing and so on. And similarly, when we increase the window length to 1024, we are going to see the more gaps, and we are seeing a different sort of, I would say, representation of the same signal. And why we do that? Why do we need different window length? Because when we use different window length, we are going to divide signals in smaller chunk or bigger chunk, and depending upon smaller and bigger chunk, we are going to include more frequencies or less number of frequencies. So when we are using smaller chunks, the possibility of having more frequencies is less, because this is smaller window length, smaller chunk. But when we use bigger chunk, then it is possible that we will see more number of frequencies or less number of frequencies. And when we do Fourier transform on those, we are gonna break up into different frequency domain, then having a different window length and so on. And that is a sort of, I would say, important in one way when we do the actual analysis, or when we feed this spectrogram to model, because based on that we are gonna feed either too much information or too less information to model, or perfect information to model, and that would help model understand if we are going in right direction or not. And then this is again the same sort of plot for different instrument, and for different instrument we are seeing different plots similar to what we saw in the waveform plots. But the one thing is same, as we move to higher window, we are seeing more gaps and sort of different representation of same signal. Then again, the most used plot would be Mill spectrogram. So spectrogram is sort of converting your again time amplitude to your frequency domain, coming to the same domain, frequency domain. And it's it uses more or less similar sort of properties like a hope length, window length. The few additional parts are minimum frequency and maximum frequency. So it's act as high pass and low pass frequency filter, you can say. So basically we are just gonna have frequencies which are in between these bandwidth 20 hertz to 16,000 hertz. So it can act as a sort of filter for us as well. So we won't worry about other frequencies except these two. As I said, human ears are perceived between 20 to 20 kilohertz. So if we just consider about that bandwidth, then I think having a removing other frequencies would be helpful, because we will know what exactly we are seeing and so on. here you can see like this is the plot for one of the instrument, and the thing is like this plot gives us idea of like how like the frequency domain is associated, and you see like these lines which basically tells us that there is some sinusoidal signal here, then the similarly like this sinusoidal signal has like this sort of frequency, like frequency on the y-axis. And again like this is like one more plot for a different instrument. And here the plot is like having too much of, I would say, frequencies all over the places. Like we can see, in all the greenish part are can be considered as one signal. So you can see like there are like too many signals present, or like too many smaller signals are present in the this 3 second of audio and so on. So I think this is like a sort of, I would say, is like a small analysis of the your data, and this would give us the idea of like what sort of window length or like hope length should be used, which can like work better on our data depending upon the visualization. If we can like clearly differentiate from the visualization itself that this is like a cell instrument, then this is like a different instrument and so on. Like the visualization speaks for itself, like we can know the difference and so on. But of course like this is not easy when it comes to like I mean, we just like use two good audio samples which shows like a clearly different visualization here, but it is possible that we might see like sort of similar plots for even if they are like a different instrument, depending upon the frequencies and like other stuff that they have. uh, so I think this is it for the and as like it is Kaggle notebook, you can like do the save or like quick save and so on. And I think we can conclude our EDA here and move to the part where we talk about more of like modeling side, like how you would model this information or like the visualization that we see or like the audio that we heard into a deep learning model, and then the deep learning model would be able to like tell that okay, this is like a guitar or this is a piano or what it is and so on. So for that we have this other notebook. Uh, First, let's go back to some of the slides and talk about a little bit of stuff there. So we saw the simple EDA, and now let's move to deep learning for audio classification. So there are a number of ways you can utilize deep learning to do the sound classification. So as first we saw the waveform plot, right, which was with amplitude to time. And when we draw that waveform plot, we use like a simply our ND array that we got from the librusar.load. So basically that's like sort of 1D array that we saw there. And when it is like 1D array, basically the data is 1D, right? So when it is like a 1D array, or you can say like raw audio signals, then you can use like a simple neural network. So let's say we just like, we know the sample rate is defined. So we will know like what would be the output size of the 1D array, or like, the audio signal that we got from librosa.load. And based on that we can just like define our input, just fixed size of input, and then like connect some fully connected lists and so on. So sort of we can use like simple neural network or dense neural network to do the classification, or we can use like 1D CNN, which also works with like 1D data. I think it's like it has been used in one of the competition, like gravitational wave detection competition a lot. So in that competition, we had like three signals, like three audio signals from three different antennas, and like when we have three signals, we can actually like combine them and create a sort of image, right? Like concat all the arrays to make a 3D or 2D array. So if you have 2D array, sort of it works as like image. But another way is like concatenating them and make a 1D array and utilize 1D CNN. So like the top solutions in that competition used 1D CNN, and like they won the gold medal and like prize money and so on. So that's like sort of one way to do the deep learning with audio signals, or like in one way you can say like with any signal that wasn't just like a like some audio which we can hear, like it was really high frequency domain audio data, so we can't hear that and so on. But we can use 1D CNN if it is like a raw audio signal. And of course, you can go with mill spectrogram, like the spectrograms that we saw, STFT or MFCC. MFCC is like another representation that you can utilize to create image out of your data, or like create image out of your 1D audio data. And when you have like 2D data, you can like go with 2D CNN, or like image classification problems, or like you can use the models like ResNet and so on. Or you can try like RNN or LSTM and so on, like they are also like a sequence classification. So sound is also sort of sequence, right? Like it moves from like left hand side of x-axis, or like a time to right side of time and so on. So it can be considered as a sequence to sequence modeling as well. And there has been a lot of work in that domain as well, like using RNN, LSTM as well for the sound classification. Of course, I have seen most of the people doing like a 2D image classification when it comes to sound classification. Like the recent concluded BERCLEF 2022, I think the top solution used CNN. I think in the last year iteration in the BERCLEF 2021 also, like people used CNN, and it was like working really well for really noisy data even. So that like there are like two possibilities. You can go with like sound classification when it comes to deep learning. In this tutorial, or like in current event, we are going to go with mill spectrogram and image classification, because I would say it works really well, and it's like a really easy to do, I would say. Then 1D CNN maybe not easy actually, but still let's say it's like easy, because I already have done the coding part. So uh, yeah, let's start with it. So first of all, like I would like to say thanks to CPMP sir. He is Kaggle Competition Grandmaster. A lot of you guys might know him already. He actually open sourced his last year top solution, like a gold winning solution. And I used a lot of inspiration from his code. Of course, not the same code. He used STFT transformer, or like he used transformers to do the image classification for audio data. We are going to use other model and so on. But thanks to him, like he gave me a lot of ideas about how you should write a code when it comes to Kaggle competition, or like how you should write a code which is like sort of really generalized in a way which can be like reused again and again. So first of all, we will use the library team. If you are using PyTorch and you have done image classification, then I must say that you might have used this team, which is like Torch Image Models library. It is a generalized API library which can give you tons of image classification model, tons of CNN. It has like ResNet, Wide ResNet, ASCII ResNet, and all other like VIT, like Vision Transformer. It has, I think, like all versions of it as well, and a lot of other models like EfficientNet and so on. Again, we are gonna do some of our inputs, like some like stratified k-fold, then like some of the metrics from sklearn, then some of the transformation from sklearn. Then we are importing torch modules, like first is like a torch, then nn module of torch, then functional, then data loader, data set, weighted random sampler. We are not going to use it, but I imported it. Autocast, then grid scaler, then we are importing beta distribution, then parameter, then we are also doing like torch audio. So PyTorch has like this torch audio module, which is more or less similar to Librosa. The thing is, Librosa works on CPU, but torch audio is something which works on GPU as well. So let's say you are doing a BERCLEF 2022 and you have some gigabytes of data to work with, sort of like 6 to 10 gigabytes of data. Then using Librosa to load each of the sound and then doing STFT or mill spectrogram would be a lot time consuming for you. So instead, you want to move the whole process on GPU, and there comes like a torch audio like library, which can help you do all the STFT mill spectrogram on the GPU, and this is gonna like speed up all the process. In this tutorial, I'm not gonna use torch audio. We are just gonna do like a simple things with Librosa, but I would say using torch audio along with your model and so on would make your stuff a lot of fast, like training a lot of fast. I will discuss that in when it comes to that part as well. Then we are using SciPy, some of the SciPy functions, then matplotlib again, then like filtering out warnings and so on. Uh, Then the of course, like the when it is deep learning, you want to be deterministic. You don't want random stuff happening or like random results generated all the time. So it is very important to seed your notebook or like your code, so that get same results whenever you run your code. So we are seeding everything first, like random, then np.random, then torch, then when it is like there is CUDA available, we want to do like manual seed, and then like backends in QDNN, we do deterministic is equal to true and benchmark is equal to false for CUDA as well. Then just like getting the device. So in torch, you need to define whether you want to work on GPU or CPU. So we use this torch.CUDA is available, then torch.device to get the device. So it will just like say, okay, GPU is available for us. Yeah, that would make stuff a lot of fast, like the training really fast for us. Now again, like constant and sort of configuration, you can say. So sample rate is same, like 44,100. Then this is path, this is actually useless, you don't have to worry about it. Then length of audio, so like we saw in the plots that it was 3 seconds, but I'm using 2.90 second, considering that there might be some cases where the audio signal is like little bit smaller than 3 seconds. So we don't want to run into a problem where we just like realize that, okay, the sound is not 3 seconds and now the code is not working. So just make sure that all the signals we get have like equal length. Then number of male spectrum, like the number of males, then minimum frequency, maximum frequency, number of FTT, then again hope length, and then like we are defining gradient accumulation if we want to do that later when we train the model, and then number of folds. Basically we are going to do like 5-fold training, which is like very common to do in deep learning. Then we are defining some of the parameters related to model. First is like epochs, we are going to do 15 epochs, batch size 32, batch size, sorry, like validation batch size, which is like double than the actual batch size. And there is like reason why we double the batch size in validation, because when we do validation we don't really need the gradients. So in torch you can do like torch dot no grades, and that would like remove all the gradients, so your GPU will be more free. And when you have like more memory on GPU, you can process more number of batches or more number of data points. So basically that's why we double down the batch size over here. Then a backbone, which is going to be efficient net. So as I said, like team offers so many different models to you. You can use like a TensorFlow efficient net version. You can use like normal efficient net if you want. Then you can use efficient net v2, or you can use ResNet and so on. So efficient net is the architecture which is like sort of generated from, I think, so you can say like AutoML, basically to optimize CNN on all the different sites like depth, width, and so on. Then this mix beta is for mix-up, but I have like actually disabled the mix-up, but I will talk about that for sure. Then threshold is for like understanding at what threshold you wanna like make a classification judgment and so on. We'll discuss that too. Then, of course, the first part is to create a data loaders when it is PyTorch. So data loaders would follow like a simple, simple this 3 step. First is like a generate label based on the name. So, like we saw there is like instrument name presenting the file itself. So you can use like the primary and secondary both targets, like, two instrument at a time, or you can go with the just like the primary one. So for the sake of simplicity, we are just gonna go with primary one. So if it is like a piano, then we will just say piano. If like piano plus guitar is there, we are not gonna say like piano plus guitar as a label. We just gonna go with piano. After that we create a data frame, just to, so like we saw that we have this whole directory of instrument and their files and so on. So it's like good to create a data frame so that you can utilize it later on to like either trace back to your data points, or like convert it to fold, and like split your data into different folds, so like on what fold you are doing good, on what fold you are doing bad. And when like on what fold the model is not working, you can actually trace back to the data point itself, like these are the instruments which are not doing good, and in that also you can like trace back to like exact files which are not working well for you and so on. So sort of help in like solving the errors with modeling at the end. uh, then yeah, like we have the data frame. It has like the path and the label, which is like sort of just the primary label that we have. Then let's generate the k-fold. We are using stratified k-fold, basically simple technique to divide your data equally in 5 folds, and so that all of the labels in each fold have like same number, and like in the other fold also have like sort of similar number for each of the classes, so that we can have like a sort of class balance in between different folds. Sometimes it is hard even using stratified k-fold to balance out the classes. So there are like different tricks, like you can use class weight, or you can scale your loss in some way to mitigate the effect of imbalance, or and so on. Then like I just saved it in trend.csv for later use. Now we have like one more column, fold, which just like tells us in which fold this data point belong to and so on. And then we are creating like this instrument code and then inverse instrument code directory, basically sort of mapping that piano has like index 1 or piano has index 0, and then like index 0 belongs to piano and so on. So this mapping is useful when you go for inference. Then you just like do the like a prediction from model, you get the softmax probability, you do the argmax, and then you get the index. But then you want to revert back to the actual label, like whether it was piano or guitar or what, and then you need this sort of inverse labeling, or like this to reverse map back to your actual label. Then torch dataset class is gonna be like our loader for like loading the data. What we will do is like load the raw audio using librosa, then we will convert like we will generate mil spectrogram for the audio, and then like we do the decibel from a decibel to from amplitude, so like amplitude to decibel function, and then we will get like decibels. Then we got like that 2D plots that we saw here. This is like sort of image that we got. So this image is like monochromatic. We want to convert that to RGB, you can say, and then like we will for that we will just like map all the values between 0 and 255. So we know that image has like a 0 as the value, like lowest value for the pixel, and highest can be 255. So we map all the like all the values that we have in this spectrogram in between 0 to 255, so that we get the perfect image, like or actual image, you can say. Because our model is trained on like ImageNet, it is like already working with images which were between 0 to 255 pixel. So converting our actual like a spectrogram into that range would help us, or like help the model understanding the image well. And of course we do like a normalization of image as usual, and then we do one hot encoding for the target. So basically we can't like just feed the index, so we do like conversion into one hot encoding. And then this is like get audio function, which does basically load the like a y, or you can say like audio data, and then sample rate for us. Then mono to color basically converts a one channel array to three channel array, or and like between 0 to 255. So basically convert our mil spectrogram into proper images for us, and it's like it's doing that by using min max of a spectrogram. So basically mapping like a minimum to 0 and maximum of that spectrogram, or like an array to 255, and then like converting intermediate values in between to like whatever mapping that they get. And then normalization, basically normalizing our array or like our image. We basically just divide by 255, and if you provide like mean and standard deviation, you can basically subtract mean and divide by standard deviation, which is like normal standardization, or normalization that's like used in conversion. Then compute mil spec. So basically this is just gonna compute mil spectrogram for us. It is using the same function that we saw in our EDA mil spectrogram from librosa, and then it is using again like power to decibel, this time to convert from like a amplitude to decibel for us. And then our actual torch loader, which is like gonna load our data. The get item function has it use so first let's go through initialization. So self.data is simply data frame, then data path is like path to data. It is not useful actually. I just have it, sort of, you can say this is like a code which I use in all other competitions, as well as in all other processes when it I have to write down the torch loaders for my task. Then target is basically target. Then we have option to add augmentation, but I have removed all the augmentation in this one, but we will discuss about that for sure. Then no calls is sort of not useful again. Then effective length, which is basically what should be length of our array, or the array that we are going to get from the audio. So it's going to sampling rate multiplied by length of audio itself. uh, and then a length function of our data loader, which is getting length. Then we use self.data.iloc and to get our row from the our data frame. Once we have the row, we have the path column, and from path column we are going to get the waveform, like the amplitude waveform. Then we just see if it is equal to the effective length that we need. So basically equal to 2.9 second or not. If it is equal to 2.9 second, then we don't have to worry about anything. But if it is greater than 2.9 second, basically we just trim it down to from beginning to 2.9 second. And if it is not greater, then it might be smaller, or equal to that 2.9 second. Then we just create this new wave just for we make this np.zeros array, which is equal to effective length. And then what we did is we generated the start point from where we want to pick the audio. And then we did from start to start plus length of waveform is equal to waveform. So basically if the audio is smaller than 2.9, then what you can do is you can add itself again to make the effective length greater than or equal to 2.9, right? So basically just if it is 1 second, then add that 1 second 2 times or 3 times. So you would have 2 second and then 3 second. And when you do that, you are actually replicating the same sound again and again in your data point. But that would help in way, because sometimes if it is a smaller audio, then you really want to use it, you don't want to throw it away. So repeating the same sound again and again would still make the sound really good data for us, and for our model. Then once we have the waveform, we compute the mil spectrogram, we convert it to actual image, then we do the normalization, and then we create our torch tensor out of it. And then we are using we create then this is sort of just a dictionary created to feed our data to our model. So spectrogram is sort of our image, so assigning the value. Then if it is the self the target is enabled, which is saying we want to target or not. We want target for training purpose, we don't want them for inference or testing purpose. Then we create labels, which is np.0 length of inverse code, basically all the instrument that we can have. And then we are using primary label, which is actual label, or the label that we got from the instrument, or the folders that we have, and assigning that to 1 in our labels array, which is sort of one hot encoding representation. And we put that into our input dictionary, and use key target as a key, and then convert that to torch tensor. And here we are using long because we want to use cross entropy as a loss. And now the modeling part. So our model is going to be very simple. As I mentioned previously, we are just going to use efficient knit for modeling. And in the slides, I want to just talk a little bit about this. So this is the model architecture that we are going to see. So we had the a raw or actual waveforms of audio. Then we did a mil transformation, or you can say mil spectrogram. Then we converted them to really good images. Then we are using efficient knit b0 as our backbone. Then as a pooling, we are using gem pooling, which is like sort of a pooling which you can train itself. Like average pooling and max pooling are something you can't train, or like you don't train, but this pooling layer can be trained. Then you use like output layer, and then you get like softmax probabilities. Now there are a lot of stuff that can, as I mentioned previously, there are a lot of things that you can do on the GPU itself. For example, we use Librosa, but if we replace Librosa with Torch Audio, then of course we can load this sound, or like we can just like load the sound or like a waveform using Librosa, and we just feed that 1D array to our model. And in our model part, we here like instead of this backbone, we have like a torch audio module over here, which will convert our raw waveform into mil spectrogram on GPU. And when it converts like raw audio to spectrogram on GPU, then the computation is really fast compared to Librosa itself, which will speed up our training process. And again, one more thing is like I talked about having mix up as augmentation. So in audio you can do a lot of augmentation, putting silence in some of the places, adding some other noises like humming noises or like other Gaussian noises. Like we must have heard like that zoo sound coming from microphones many times, and that can act as one of the augmentation for you. And of course you can mix up like mix up two instrument or three instrument, and like convert new labels for them based on the mix up percentages of two signals. And that mix up can also be done on like GPU itself. So when you do such operations which are like more on the GPU side rather than CPU side, your training efficiency would increase, as well as you would like see like significant speed up. Of course there is like sort of like this issue with GPU computation is always there, like they are sometimes not deterministic, so you have to make sure that everything is deterministic. But using GPU as like your main computation would give you benefit of doing a lot of stuff fast. Now in modeling, I said that we are going to use gem pulley. So this is like a code to do the gem. It does the forward pass and uses like this gem function, which does like average pooling and then power of p and like convert our like sort of act as a pooling layer which learns, or which we are going to like train while we train the model as well. Then mix up is like sort of mixing up two signals. Here you see like only x and y. So x is our input batch and y is our targets for that entire batch. So when we have batch, let's say we are going to like use 32 as batch size, we have 32 data points, and we can mix up them with each other, right? Like I mix like the signal at 5 index with a signal which is at 7 index in the batch, and that can work as a sort of like augmentation for me. And then like when we mix up, we have like this array, or like in like the x which is like mixed, and we have like two labels y and yb. Basically like you want to know like how much percentage was there when we mixed two signals, like 50% of one signal, 50% of another, 75% of one, 25% of one, second signal. And when we use 75-25 split, you can say like ya would become our 75% target one, and yb become like 25% target two. And this is like a NN module, so basically this goes on GPU as well, and then like we can have like a lot of speed up because of this. Now like the backbone class, so in the slide we also see like we are going to use backbone. So this code is like taken from CPMP sir, and he like created this really good code. You can see like if there is resonate, then you compute the output features like this, if VIT then this, and so on. So it basically works with any model that we want to utilize. Like we are going to use efficient net here, like which is over here, but efficient net itself has a lot of variation, like torch, tensorflow, then efficient net v2 and so on. But the code would work with any of those model, and it is like thanks to him. uh, then again we are using like this then we are defining our actual model, like the model we are gonna use like backbone, then a number of output dimension, then loss, if we want to like compute loss or not, then mix up, if we want to like do the mix up or not, and pre-trained, which is like a sort of telling that we are going to use a pre-trained model from teams, or like which is on already trained on ImageNet. Then backbone name, then loss, again like defining those functions. And then we use this self.backbone as our backbone class, so which we saw previously here. Basically giving the name and like name of the model and whether we want to pre-train or not, and then our pooling would be like gem, and then like our head is like simple and n.linear like backbone dot output features and like output dimension that we want, and then loss function is like a cross entropy loss. And if we want to mix up, then we can do mix up using the mix up that we already have created. We are also computing loss on the GPU here, so you can see like in the initialization of model I'm adding the loss. So basically when we get the inputs, which is like input directory in our loaders, so it has like spec and target, and actually this should be removed and it should be like put somewhere over here, but it's fine for now, I think. This like spect is our image or like a spectrogram, then target is our target. If we have enabled the mix up, then it would do this mix up, and like it would do the forward pass to model. Actually this should be like this, so that we do forward pass with mixed x and not just like the normal x, but it's not enabled, it's false. And then like if mix up is not, then just like do the normal forward pass without any mix up, don't do mix up and just like do the forward pass. And if it is like there is backbone as VIT, then it has like different outputs. It is, if the backbone is not VIT, then you have like outputs like this, and if you are using like a vision transformer, then the output is like a different, and which is like a sort of this, you get like two embedding output from the vision transformer, and you want to like sort of add them and then pass that to your head and so on. Then just like pass whatever output we get from like our pooling here, from pooling whatever we get to our head. We are doing indexing over here, so basically when we get from pooling, we get 3D tensor, but we can't feed 3D tensor and get like a 1D probability or like the probabilities from our head, right? So we want to like just do like we want to just use 1D output from our pooling, so we just like indexed it in a way where we just don't use the second and third axis, we just use first two. So first axis is always like our batch size, and the second axis is always like our normal like output from pooling in one channel, or like you can say in one direction. And then logits like compute using head, and then we create output dictionary basically, which has like logits like this. And if self.loss is enabled, which is true for this case, so we are training, so we want to compute the loss, then do your loss computation as well over here, like logits.softmax would convert to softmax, then max would give us the maximum of it, and then put that into your output dictionary. So basically computing your like loss as well on the GPU, so that would also like speed up your training process when you compute your losses on GPU. And then use like this output dictionary to add target as well, so that you have like loss, logits, and targets, three things outputted from your model. And if you disable the loss, you can just output target and logits. So sorry, you don't have like targets in case of inference, so you can just like return this dictionary with logits only. And then like a normal training of PyTorch. So this is gonna be like you can say like normal training in PyTorch. How we do it? We are using autocast, which is like like a automatic mix precision. So basically speeding up it again like speeds up the training when we use automatic mix precision. So first we do the forward pass, where we feed like input dictionary from the loader to our model. We get the output dictionary. In the output, I talked about three things like logits, loss, and target. So we first got the loss and we did the mean of it, and then like convert it to NumPy. And like this is NumPy loss, and this is like actual torch tensor loss. So like don't mix up them together, and then like use the scalar dot scale loss dot backward to do the backward pass. So basically this scalar is a gradient scalar from PyTorch, which basically scales the gradients and losses for us, and then it does the backward pass. Then if you want to like do gradient accumulation at certain intervals, then you can use like this gradient accumulation, which is like 1, so it's gonna like happen all the time. And then like we do the step like optimizer step, then we update the scalar, and then we do like model dot zero grade, which is basically like removing all the gradients from the model, and then again like appending the loss into our train loss, and then this smooth loss is basically uh, like a loss computed over like a last 100 uh, like iteration, or like last 100 batches. So basically we want to just like keep track of both the things, like the loss for all the batches, as well as loss over 100 batches, so that we can print it, or like utilize it to like print over our progress bar. Then in Valleypoke, it's like we do this with torch.no grid. So I mentioned like having double batch size in validation. The reason we can do that is like using this thing with torch.no grid. When we do that, we remove the gradients of the model, so that our GPU has more memory. And when we have more memory, we can load more number of batches on GPU, and hence we double down the our batch size in validation. Then again, here also we are gonna like do the same forward pass, like feed our input dictionary, got the output, got the logits, and got the loss, and here we are also getting targets also, because this is validation. We want to know like the performance of our models computed at the end of this epoch, right? So basically we query everything like logits, loss, and target. We put logits into logits after doing softmax, target into target, because they are already like softmax, or you can say like they are already one hot encoded. Then append your validation loss into this well loss, and then like compute smooth loss over last 100 batches or 100 iteration, and then at the end like return these logits, targets, and your validation loss. So we are here like taking mean of like all the losses that we have like accumulated over the time, so that we exactly know like what was the mean loss, or like loss over uh, our validation. And then targets and logits would helpful to do the evaluation after first epoch or second epoch, or after every epoch basically. And then save checkpoints is like basically saving everything. We can save model like this, optimizer, then scheduler, then scalar like grade scalar, and number of epochs as well if you want. And then it will like do the checkpoint saving for us. And load checkpoint is basically inverse of it, you can say. It basically creates everything first, like a model, then your optimizer, scheduler, scalar, and then we like load the checkpoint from the saved pt file, and then like we do the state dictionary load for model, optimizer, scheduler. So basically in case we stop training at certain epochs, we still have the model, optimizer, and everything, and we can like resume the training from that certain point, because we have like retained state of optimizer, scheduler, and everything, so they will start from exactly where we stopped it. Now in training, like it's very simple thing, right? Like it's like basic backbone of all the deep learning or machine learning processes. Like you do the training, then you validate, and then you like sort of see the performance of your model over the time, compared to like everything. Like you just keep track of like how the loss was on first epoch to like n number of epoch, and so on. And then it basically starts the training for us, and once the training is over, it's like gonna do certain things for us. So we already accumulate the logits and targets for our validation. So once we have everything like like logits and targets, what we can do is basically compute f1 score, precision score, roc auc score, and like we can basically actually print them if we want. And you can do at the end like a plotting as well, like you can uh, plot like loss versus epoch. So we also accumulated all the losses, right? So just like as we are accumulating loss, we can uh, plot the losses, and then we can also plot the matrices like f1 score, precision, auc for validation. And at the same time, I have also added like confusion metrics. So basically that will also tell us the uh, like how we are doing on the confusion metrics, or like where we are getting confused, and so on. So I think this is it. I will show the results. I will have to like open the the other notebook that I had, like which is same version of the same notebook. Let me do that. Okay, I have it. So the training is going on over here, but let's say after training, what you will get? You will get after like 15 epochs, you get F1 score of 0.70, precision score of like almost 0.71, which is more or less similar to it, AUC score of 0.92, which is really good, and you get this sort of confusion metrics for all the predicted label and your true target. We can see like so many of them are like classified correctly. Of course, some of them are like misclassified because like it's really hard problem to like solve, and I would say like we are not using any fancy stuff here. We are just doing basic modeling. We are not using any augmentation. It's just like very simple modeling. So it's like a sort of like we can see the results are also like sort of not that. I mean, they are good, but we are still getting a lot of confusion in between like different instruments. If we see loss versus epochs for fault zero, then this is the loss for train and validation. We can see like both of them are going well. There is no sort of I can't see any sort of overfitting here. Like the validation and train loss are going perfectly fine. And when we see like a metrics, then we can see like AUC started at 0.7 and it went to like 0.92. Then precision recall, precision and F1 score went up to like 0.70, and we see like a really good improvement over the time. Of course, if we train, we might get really good results like for longer, more number of epochs, and we can add like augmentation, like mix up, which we disabled in this one, but we can enable it and like let it run. Similar results can be seen on fold 4, I think. Yeah, this is for fold 4. And you can see like again the like number of confusions here. At the bad bad result would be for this, in this particular instrument we are like sort of misclassifying it a lot. And this is where we really need to understand, or like the if we have like the save data frame which we created trend.csv, we can go back to fold 4 and particularly at this instrument and like track down all the files of this instrument which are in fold 4 and listen to them ourselves and decide like it's really confusing or not, and so on. And if we really want to like train on them, we can like do certain augmentation for those only, for particular fold and so on and so forth. So that helps like in sort of like backtracking your errors and so on. So I think that's it for like the code and other parts. uh, so yeah, I think thank you everyone for listening to me for non-stop for an hour or so. And I would give mic to Ayan.
Yeah, thank you, Urvish, for such a useful session. Like actually, like I was taking notes throughout while you were talking the process and the approach that you took, because it's really good to see that without doing any super fancy, right? Like it's usually what do people do? It's like they go to very super high tech things, and somewhere the main essence of the things get vanished. But the
Yeah.
way you have approached it, and the simpler approach, like I would not say it's very simple, but definitely the folks who are working, they definitely know the approach, how to move ahead and all those things. I definitely took notes, and it works well with me. So thanks for that. Thanks for the session. And we have a few questions, like
Yeah, sure.
yeah, which pre-trained model is good in audio data in your experience? Like I think this question is on an overall basis. Like maybe if someone wants to work on an audio domain, which pre-trained models work good, or your experiences around that?
So I took part in like I would say all the bird call competition, like except the current one. So in the first competition we saw like CNN model like a ResNet with attention was really good. So you can say ResNet worked really well in that. SE ResNet also worked really well in that competition. But when we moved to the last iteration, like BirdClef 2021, we saw EfficientNet V2 or and EfficientNet works worked really well. So in nutshell, there is no, like I would say, we exactly know like whether the efficient net or ResNet are gonna work. But the thing is like it's like sort of trial and error. You will have to like try different models. Some things like attention would definitely work. Actually, CNN with attention were the like all the time they were the competition winner. Even the CPMP sir, he used, I think, like swing transformer, so that also has like sort of attention, right? So CNN plus attention combination works really well, I would say. What CNN? That's like sort of something you have to try or like experiment with. You can try with ResNet, SE ResNet, and efficient net. Those are like simpler one, I would say, or like easy to utilize and so on. So that would be my take on that.
Yeah, got it. So, and it's like you mentioned a good point that most of the winning solutions have tried to utilize those things. Like those came up with good results. That
Yeah.
makes sense. Yeah. So, like another is, how do you do a memory management when you're especially working with audio data?
So like when we are working with audio data, I would say memory is not that much issue. Like the RAM, like the CPU memory, that's not a big issue because we are just loading a single file, audio file, right? And they are not gonna be like some gigabytes, right? They are just like some, like 1 MB or even less than that usually. So even if you load like tons of data in the memory, then also like it's not gonna be an issue. If you like fall into the memory issue, then the idea would be like converting your like float 32 to maybe like float 60, I mean float 64 to float 32, and like reducing memory that way. That would be the only trick, I would say. Moving your computation to GPU would be another thing that you can do to speed up the process or like manage the memory, because on GPU you can use like automatic mix precision, which is already like reducing your float 32, or like float 32 tensor to like float 16, and even like less than that sometimes. So that would like help in memory management. But I would say it's like very hard to run into memory issues. Like we worked with I said like I participated in two of the competition, in two iteration, and they had like 20 gigabytes of data. But even in Kaggle notebooks, I was able to like train the models and everything properly, because it's like loading a single audio file or like 32 audio files in memory, which is like very small in terms of memory.
Got it. So it's like like getting to a position where you hit the dead end would be a little bit of less of challenge when you
Yeah.
work with this. But when you, in case you hit, you definitely have good optimizing solutions, because like
Yeah.
coming to 64 to 32 and all those things definitely work. Like it's not only for specific these things, but
Yeah, they are
overall, like
generalized. Yeah, they are
yeah,
like
yeah,
they it's like trick which is like used in across, I would say, all the Kaggle competitions. I have seen like
yeah,
people doing
yeah,
that
yeah.
many times. Yeah.
Yeah. And how do you effectively approach augmentation, like in audio data and all those things, like just from your own analysis or from your own experience, how do you think maybe one should approach augmentation, or your tips or experiences around that?
Yeah, so in that, I would say there are multiple augmentation available. First of all, there are libraries like augmentation, I think, which is like sort of like library like augmentation in images. Uh, so uh, so like you can use number of things. First of all, I said like you can add silence in your data or like in audio file, and that would act as augmentation, because your model will see like silence for some time and then some sound at the end or at the beginning, and it is like sort of augmentation. You can mix up two sounds, like as I mentioned, like you can have like two instrument mixed together, but you can also mix like other noise like humming noise, right? Like just sound into your audio, and that would act as augmentation. So you start with simple augmentation, just like what we do in images, like in images we do like a sort of rotate or like horizontal vertical moves and so on. So in audio data you can't do that actually. Like you can't move mil spectrogram to horizontal or vertically, because that would change like time and frequency axis, and that doesn't make sense, because like changing axis is like converting just the domain,
Hmm.
like
Hmm.
changing
Hmm.
time to frequency and
Yeah,
frequency to
completely to get opposite, right? Like
yeah.
yeah.
So that
Hmm.
doesn't make sense. So what you can do
Hmm.
is like you can just like add silence, then like add some other noises like a humming sound and so on. Then like at complex part you can do like a mix of two audio, and then like when you do this augmentation you have to do them or when you like load the audio files itself, and not on the spectrograms or STFT of audio. You cannot like do like a mix of to mil spectrogram, because that doesn't make sense. Like, as
Yeah.
I said, it's like transformation from time to frequency domain. And when you like mix up the mil spectrogram, it's like that's like a not something that should be done. So you
Yeah.
move like
Yeah.
that from simpler one to like complicated and so on.
Yeah, makes sense. Like, how do we transition from the simpler parts? Like throughout the presentation, I was also mentioning you, right? How do you went to the simpler parts and simpler processes that helps us to understand the things better. So yeah, augmentation this way definitely makes sense, and we could not completely replicate the things we do in images, because images still we can get something, but this is very time sensitive. When I talk about audio data, you have the frequencies and all those things, and you cannot rotate and just do, like, it would be
Yeah.
completely different thing like otherwise. So yeah, like, good suggestion on that. Another question was majorly around, like, if someone wants to get started with the audio section of data science or AI/ML, right? Like, you recently saw like a lot of the competitions on Kaggle also came up on audio, and
Yeah.
like also on other platforms, like audio is getting a lot of, I would say, highlight, or like, I would say, a lot of attraction, like
Mhm.
and maybe a lot of the organizations are also working towards audio data, right? Like, you have
Yeah.
those, like, because tabular data somewhere stabilizes, but audio data is something which the companies are also looking forward to explore, because they have
Yeah.
chat conversations and all those audio conversations, and they want to bring certain things out of it. So like, if someone wants to start in that direction, like if someone wants to go into audio, or someone wants to dive into the research for audio domain, how do you suggest, like, any specific source or any pathway that you could suggest to those folks, though
So
it's very very difficult to
yeah.
pinpoint the resources, but yeah.
So I would say like start with Kegel. That's my there was time when I didn't do any Kegel competition back in 2019, and then I started with like one and then second and so on, and then I came to like all the different things like NLP, then audio data, then images, and so many different things. So I would say start with Kegel. The reason is that on Kegel there is always like like every year there is all at least like one competition in audio, and it might be like from like the same host like Birdclef. So they did like three competition up to like three consecutive year, but and in all of those competition, the data set was more or less like I would say like similar, like in terms of labels, like it was bird calls and you have to like identify the birds, like that's the simple gist of it. But the actual data, like the inside data, that was changed, like based on locations, based on the like the instrument they used to collect the data and so on. So you will learn like about all that smaller details, like where there was like in the first iteration, I think CPMP sir used very simple trick, like in the entire audio file, like like 30 second of audio file, he just used first 5 second and last 5 second of it to train the model, and discarded the rest. So it is very simple trick, like just use first 5 second audio, last 5 second audio, very simple thing, right? And like it was sort of like a winning solution for him, like because nobody knows like exactly like how annotators label them, right? So it's obvious, like when you heard the sound, you start from the beginning, and when you hear like the piano sound, you just label it piano. You won't like bother to listen to like up to 50 seconds or 1 minute of the audio. And so if you want to like really learn like I would say like from beginning to up to an expert level, then you should definitely do the Kaggle competition or like read the discussions and so on. So they have always the resources like from where you can like learn about the STFT or like mil spectrogram and like waveforms and so on. And then of course the competition is always there, which is like where you can apply the models and like train your models. You can apply the different tricks from you learn from the previous competitions, or like if you have good ideas, you can apply your own ideas and so on. So I would say like Kaggle is definitely like one of the platform.
Yeah,
Apart
yeah, yeah.
from that, you can maybe like refer to some books. I haven't actually like read any book or any other resource like apart from Kaggle competitions for learning like any like audio classification or deep learning with audio. So for me, I would say Kaggle was the only platform or like thing that I would do for now at least to learn about audio data.
Yeah. Makes sense. Why this is important? Like, otherwise people go to blogs, people go to certain other videos, but they don't actually get the hands-on practice. Like, when you're
Yeah.
trying to get into these kind of things, definitely it's not that you have to come into the top tiers. It's like, just at least get started and get your hands dirty at the first place. So yeah,
Yeah, and when
that was a
you
good suggestion.
Yeah, and when you like read the solutions on the Kaggle, you would realize there are like always smaller details that like we miss out, and it doesn't come up to our mind, which can like come up to grandmasters, and that's like something that I would say like that's very helpful in learning, because when we do like a lot of I mean, like a lot of people have done image classification, right? Like it's very simple stuff and so on. But there was this competition where like a winning solution of like all the grandmasters, they use stride is equal to one in their convolution layers or like in their models. And the idea was like a stride is equal to one helps in learning the lower level features. And this is like something that I never heard or never read anywhere. And this is
Mm.
like something that when you really dive deeper, then only like come to somebody, and
Yeah.
then only you
Yeah.
realize. But even if you haven't even if I haven't dived really deeper into CNN, I know the trick because I read the solution. So it's like even if you haven't done too much on the domain, or if you haven't done like so much of research in the domain, still you would learn a lot of stuff just by reading up the solutions or like discussions from the grandmasters and so on Kaggle.
Yeah, yeah, like it's building up on their learnings, like
Yeah,
whatever they have learned, whatever experience they've brought in front of you, you're trying to use those learnings. So
yeah,
those were the major questions that we had, and thank you, Urvish, for taking the time out. Like it's a early morning in in Canada,
in
so
Canada.
like still you figured it out. Thank you so much, and
Yeah,
I
you're
hope,
welcome.
yeah, I hope the community members get a lot of learnings from your session. And like we will share the slides and the notebook links. Maybe in case you want any further help, you can connect with Urvish on the LinkedIn, on his LinkedIn. So thanks all of you, stay safe, bye bye.
Thank you guys, bye bye.